Hey everybody, here is our next section about exponential and log graph transformations. They're going to follow the same pattern as we've previously talked about in other graph transformations. It says up here at the top, I went ahead and listed a few that we've done. It says transformations for logarithmic and exponential functions is the same as previous transformations we've done for functions such as cubics and radicals. Professionally, these transformations are what help researchers understand how to interpret their data, which are used in biology, finance, and engineering. Up at the top here, I have some parent functions. This one is exponential. And you can tell because we have that horizontal asymptote right there. And then this one is log. And you can tell because we have that vertical asymptote right here. They do follow the same transformation equation as we've done before. We are going to go through these notes as if you've done this before because we have covered these generic-ish equations for transformations for 4 different functions now. This will be the next set. And then just a reminder up here at the top, the inside-outside part. Remember, if you have something that's inside the parentheses, that is going to be a horizontal translation. And if you have something on the outside, like A and K, that would be vertical. I'll put that in parentheses, so H and then A and K. For these ones, we don't have B. B is normally another horizontal dilation. We're not doing that for these because these have our base, and the way the base works differentiates between them. Perfect. So look in here. Here is a list of all the words that we're going to use within these blanks. I wanted to give you a chance to see if you could fill them in on your own. There we go. Each of the ones that have a little bullet point, so these ones are going to go in a blank. And then here it says casual words to add under the blanks. These are just slightly less mathematical words that would also help you understand what's happening. So go ahead and pause, see if you can fill it, and you're going to use every single word slash every single bullet point. And then when you're ready to check, come on back. Go ahead and check your blanks. Here they are. I will go over each box one at a time and we'll make sure to label what those transformations are within the graph as well to really help you see what's going on. I'm going to go first with the A. So A is the first row here. In our first box, it says the value of A can help you figure out the vertical reflection. Positive A is our parent function. That would be the dotted line. So I'm going to go ahead and label that. Positive A is here. That's kind of hard to see. Let me do a thicker pen. I'll do it in black. There we go. So positive A is here, negative A is here. You can see it flipped over this way. That is reflecting over the x-axis, like you can see right here if you have a negative A. And it also changes from increasing to decreasing. You can also see that reflected here on the log graph. This is a log graph with a positive A, and then it flips over to this graph here with a negative A. So it was increasing like this, and now it's decreasing like that. And you can see that right here. This is our negative A out here in front. Perfect. Next up, we have actually changing the value of A. So A can either increase to make our graph steeper, which is called a vertical stretch, or it can decrease to make our graph compress, which will be flatter. I have the pictures here. As before, our dotted line is the original. So if we have these, this is just a parent function, so our A value will be 1 for both of those. In our next one here, here's A, that is a 5. You can see when A goes from 1 to 5, it becomes much more steep, right? It was flat like this, and now it goes like that. And here on this one, A was 1, and the new A, here we go, is 1/4. I know this one kind of looks like it's shifted to the right. What you're going to look at is right there, how you can see that it went flatter right there. So it was going like this, and now it's going like that. And for all these, I did include how to do that algebraically if you want to pause and read through that, how to do it without having to look at the graph. Our last two here, K is our last vertical change. We just went over four different vertical things. Here's two more. And then H is our only horizontal shift. This one says the value of K can help you figure out the vertical translation of the graph. As K increases, we shift up, and as K decreases, we shift down. Here is the picture. These would have a K value of 0. K is 0. And then here for this one, our K is 5. And for this one, our K is -3. And you can see pretty easily here, it increased this way or decreased this way. For exponential functions, remember we already talked about it on the last set of notes. I'm going to go ahead and highlight that. Here is our original horizontal asymptote. And you can see with K equals 5, here's our new horizontal asymptote. So that asymptote changed from 0 to 5 because K is the horizontal asymptote. I'm going to put that down here at the bottom. There we go. And that's only going to be true for exponentials, obviously, because horizontals, because logs don't have a horizontal asymptote. Good, let's look at the last one here, which is a horizontal translation. The value of H can help you figure out the horizontal translation. As H appears negative, you shift right, and as H appears positive, you shift left. The reason we're phrasing it like that is because H, the horizontal translation on the inside, is always going to be the opposite of what it actually looks like. Because we have a negative sign, that belongs to the function. What I mean by that is, here, this is really x minus x1. This is really x minus x1. So if it ends up being a plus, really you're doing this, x minus a negative, like that. If it would help you right here to mark that, always opposite of how it appears. There we go. So looking at the left one, our original H value would just be 0. And here our new H value, you can see it went this way 3 spots. So our new H value is -3. You can see here it appears to be +3 because it's going to be the opposite of what it actually looks like. So when it appears positive, we went to the left 3 spots. Put that right there. Right there. And then over here is our first one. This is an H of 0. And then over to here, we shifted this way, and this would be an H of 3. You can see it appears -3, but the negative sign belongs to the equation. So because even though it appeared negative, we did go in the positive direction towards the right. These also are telling us where our vertical asymptote is. I think I forgot to tell you that on the last set of notes. Sorry about that. Our original, I'm going to write that on here. Here we go. Our original vertical asymptote is right here at 0. And the new one you can see is right here at 3. Let's put that down here at the bottom. H equals vertical asymptote. And this is only going to apply to logs because exponentials don't have a vertical asymptote. And there you go. Moving on. Here, this is a page of us practicing, seeing if we can identify what happened with our graph and then actually graphing it on the picture. I am not going to ask you to graph off the top of your head. You just need to type in the calculator and find the points on there. We'll do one of them together and then you can try the other ones. Example number 1, I did make a faux pas. Here we put b as 1.5. And so you could assume this is that, or it could be different things. It could also be something along the lines of something of this. You never know. That's wrong. But so you never know if it only has one number, how it splits up the number here. So what I'm going to tell you, I'm just going to give you one for free because that was my bad right here, it is going to compress. So the parent function is 2 to the power of x. This is smaller than 2, so a decreased. And that's called a vertical compress. So it's going to be kind of hard to see on the graph. I'm just going to tell you that's there. And then here we have negative a. That means we're going to have a vertical reflection over the x-axis. And then here, this is our k. And then remember, k is actually our horizontal asymptote. So we're going to have a horizontal asymptote of negative 3. Let's do that first. So I'm going to draw a dotted line at negative 3. There we go. Now our graph will either be up here or down here. Remember, it's going to be either above or below our horizontal asymptote, just like our logs are on either side of the vertical asymptote. Now what I want you to do is we're going to graph this in our calculator. So go ahead and get out Desmos. You can use your phone, you can use your computer, whatever works best for you. And we're just going to type it in just like that. Just a reminder to get out of our exponents, we're always going to push the right arrow. And here is our graph. Now I'm going to find a couple dots on here. I have a y-intercept of negative 4. Any of the other dots, I don't know. I'm going to have to find them. So I'm going to look from negative 10 to 10, because that's what my graph says. Looks like we're getting real close to that graph at negative 3. So I'm just going to put a dot real close to negative 3. And then we'll see if there's anything that's really close that makes our dots kind of small. Well, I don't see anything. We're getting real small real fast. So the easiest way to do this without me sitting here and annoying myself by doing this 1,000 times is open up a new tab here, push plus, add a table. And then what we're going to do is actually type in, see how it has x sub 1 for our table. We're going to do that x sub 1 on our graph. You just push the letter 1 after your x. And I'm just going to copy what's in our top row into this table for y. Like that, minus 3. And then you should be able to type in any number you want, and it will give you the y value. Eventually, if you type enough, it will start giving it to you automatically. You can see it's doing that for me here. And I'm going to stop there because that's as far as we go, where we can still see our graph, because our graph goes to negative 10. Here is our table. I'm just going to look for some points that make sense here that I could round close. All the ones that are negative look really close to negative 3, but I do have at negative 2, it's at negative 3.44. That's really close to 0.5. Let's do that. Negative 2, we'll just call it negative 3.5. And then we have 0, negative 4. I also have 1 comma negative 4.5. And then let's see. We could do 4. 4 is really close to 8. It says negative 8.06. That's basically just 8. So 4, negative 8 would be right there. And then I can just connect those dots. I'm going to use a highlighter. Let's pick something that we haven't used yet. Here we go. And there we go. And that is how you do it. Let's do another one. Here, we'll try this next one as well, and then you can try the bottom two. So on example number 2, it says identify each transformation and sketch a graph. I'm going to label, here's A, H, and K. A is a 3. That means it increases our parent function. A is 1. And if it increased, that means we have a vertical stretch by a factor of 3. Inside this horizontal change, it says x minus 1, so h is actually positive 1. It's the opposite of what it looks like. So if it looks like a -1, you're going to go right one spot. And then K here is +3. That means you went up 3. Go. And the last thing I want to do here is write down my vertical asymptote. I get my vertical asymptote from H. That's going to give us our vertical asymptote at X equals, and then whatever number H is 1. So let's go ahead and put that on there. I'm going to do that first. There we go. Perfect. And based on what I'm seeing, it says it's going to move right 1. So I'm going to go this way 1. It says it's going to go up 3. And it's going to be stretched by a factor of 3. So I think it's going to look something like that. That's my bet. So let's go ahead and graph this in our calculator. Remember, you can use your phone, a computer, whatever you want for decimals. So I'm going to close everything I have, and then I'll just retype it now. So I have 3 times the log of x minus 1 plus 3. I'm going to go to functions. I'm going to scroll till I see the word log. There it is right there. I can either pick log or log base A. Here, I don't have a base. Remember, that means I have a base of 10. I don't need to put the 10 here. I can just type it in as a log. That's perfectly fine. And then in the parentheses, I have x minus 1. The biggest concern I have, especially after our last test, is making sure we type this in correctly. See the parentheses close now. So what I'm going to do is push the parenthesis button to close those parentheses, and then make sure my +3 is outside of the parentheses. And there it is right there. Okay, so you can't tell if I'm right yet, but what we can do is take our table. So I'm going to go here. I'm going to push the plus sign, push table. I have x1, y1. What I'm going to do up here is change my x to x1. All you do is right behind that x, you push a 1. And it will automatically go down there like a subscript. I'm going to erase that y sub 1 and then just type it in exactly how it is. If you're doing this on a computer, it's actually easier for you because you can just copy and paste. I can't copy and paste on an iPad, so there's log. There we go. Log x sub 1 minus 1, close parentheses, +3. And then I'm going to try to click over here. There we go. And I'm just going to type in what we have. Our graph goes over here from -3 until 15. So I'm just going to type it in there. Keep clicking. There we go. Now, it was undefined until 1, and we knew that because it doesn't exist, right? These are restricted values. We start existing over here. Our first point is 2, 3. So I'll put a dot at 2, 3. That's right there. Next I have 3, 3.9. 3.9 is very close to 4, so I could do 3, 4. And just a reminder, we're estimating here because our graph dots are so small that it doesn't make a huge difference. If you have a bigger graph, obviously you're going to try to be as exact as possible. Let's see, I got a whole number at 11.6. Go. And then the end of our graph is 6.4. I'm going to put a dot there too. It's going to be a little less than half. Probably like right there. And then I could just connect them. Let me get off that. There we go. And there we go. I'm not trying to toot my own horn, but that's pretty much what I said it was going to look like. You're welcome. Perfect. There we go. So on the last two, go ahead and pause, graph them using your calculator on decimals, and then graph them onto the paper, and come back when you're ready to check them. Just a warning, number 3 is going to flip funny. It's going to go this way. Don't worry about that. It's just because this is a 1/3. It has nothing to do with anything else. When you're looking for A, H, and K, remember this is A. Ignore B. It's not going to make a difference that it goes this way. Okay. So graph, and then come back when you're ready to check. Okay, here we go. On example number 3, Our parent function was 2 to the power of x. You can see it flipped around. It flipped this way due to this being 1/3. Like I said, we're not going to worry about that right now. We're just going to look at A, H, and K. A went from 1 to 2, so we had a vertical stretch. H is 1, so it shifted right 1. And then there was no K, so K did not have a change, which means we kept our horizontal asymptote the same. As you can see, they both flatten out at y equals 0. And then obviously we got these dots from graphing in our calculator. And then number 4, A was a half, so we got smaller, so we had a vertical compression. It's got to be flatter. Our H value, we shift left 2 because it looks positive, so it actually is negative. You can see that right here. Number H is our vertical asymptote. You can see that right here at -2. And then shifting down 5 because our K was -5. And then obviously, again, that's what we got from the calculator. And there we go. Hope this helps. Bye.